This is part 10 of the series, Applications of Differentiation. In this part, we're going to continue our discussion on concavity, and we're going to introduce a new term. I want to investigate, once again, our dynamic graph. Here's a function. Here is the tangent line to the function at some given point C, and we're going to move this point along the function. Once again, notice that the slope of the tangent line is decreasing, and then it changes to increasing. So we learned that when the slope of the tangent line is decreasing, the function is concave down, and when it's increasing, as it is on this interval, it's concave up. But notice there was a point right in here someplace where the function changed. The slope of the tangent line went from decreasing to increasing. And that is the particular point we're going to be looking for. And that point is called a point of inflection. So let's look at that in greater detail. So the definition of point of inflection: let f be a function that is continuous on an open interval, and let c be a point in the interval. So this function is continuous on an open interval, and there's a point C inside the interval. If the graph of function f has a tangent line at this point, CF of C, then this point is a point of inflection of f if the concavity of f changes from up to down or down to up at that point. So again, on our dynamic graph, we saw that at that point, the slope of the tangent line was changing from decreasing to increasing. Or you could have another point of inflection if the function is changing from increasing to decreasing. And this theorem states that if CF of C is a point of inflection of the graph of f, then either f double prime is 0 or f double prime does not exist. And we saw that in our examples when we were testing for concavity. So let's go ahead and look for points of inflection. So in this example, we're going to determine the points of inflection and use them to discuss the concavity of this function. So as usual, we will take our first derivative and then our second derivative to determine this. So f prime of x equals 4x to the third minus 12x squared. There's our first derivative. F double prime is 12x squared minus 24x. So now we have our second derivative, but we've got to think about this for a second. We learned from points of inflection, the definition of points of inflection, that the concavity has to change from negative to positive or positive to negative, or up to down or down to up. That implies that not everywhere where the second derivative is 0 or undefined are we going to find points of inflection. So we've got to be careful about this. So we're going to go ahead and find what we're going to call potential points of inflection. And those in this function are going to exist when this function equals 0. So let's go ahead and set this equal to 0 and factor out a 12x. That gives us x minus 2. So we can see that our potential points of inflection, PPOI I'm going to call it, are 0 and 2. And I say potential points of inflection because we're going to determine now if the concavity of this function actually changes at these points. And this is what's going to be very, very closely related to what we did with the first derivative test, except in this case we're going to be using the second derivative. We're not going to be using critical numbers. We're going to be using these potential points of inflection. So our anchor values here are the potential points of inflection, 0 and 2. And we want to have test values on either side here, just like we did before. So -1, 1, 3. And now we're going to test the second derivative at these test values to find out what our concavity is. So when we substitute -1 into our second derivative, we get a positive number. So this is concave up. Put in 1, we get a negative, so we're concave down. And put in 3, we get a positive again. So yes, in fact, concavity changed from up to down at 0 and from down to up at 2. So these are points of inflection. So our points of inflection are 0, 0, because when we put a 0 into the primary function, we get 0, and 2, 0. And those are our points of inflection. So let's move on to the next piece. So here again, we're going to find the points of inflection of this function and discuss the concavity of the graph of the function. So f prime of x is 8x to the third minus 8. And then the second derivative, 3 times 8 is 24x squared. The derivative of 8 is 0. So there's our derivative. Set this equal to 0. And we can see that x is 0. So our potential points of inflection are simply 0. So let's go ahead and draw our line. Put our anchor point at the potential point of inflection. Test value at -1 and 1. When we take a -1 and put it in here, -1 squared is 1, 24 times 1 is positive, so that's concave up. And when we put a 1 in, 1 squared is 1 times 24, concave up. So as we can see, even though we had a potential point of inflection here, concavity did not change at that point, and therefore this is not a point of inflection. So we have no points of inflection in this function. All right, let's move on to the next piece. In this section, we're going to talk about a theorem called the second derivative test. And what the second derivative test does is it gives us an alternate way to find extrema of a function on an interval. And it says, let f be a function such that f prime of c equals 0, and the second derivative of f exists on an open interval containing c. So it's saying that f is a function that has a tangent line equal to 0. If f double prime of c is greater than 0, then f has a relative minimum at that point, cf of c. If f double prime at that point is less than 0, then f has a relative maximum at cf of c. If, on the other hand, f double prime of c is 0, f may still have a relative minimum or maximum, but you would need to use the first derivative test to find them. Now this theorem can be useful if you happen to be in a situation where you have the second derivative function, but you don't have the original function or its derivative, and you still need to learn something about the behavior of the graph of the function. Let's take a closer look at this. Let's look at it visually and see if we can make some sense of this theorem. So here we have a function. This is the primary function f, and this is its derivative function, and this is the second derivative of that function. Now, if we take a look at some point C, we can see that here is a maximum value. And if we look at the value of the second derivative, you can see that the second derivative is negative. And so if you recall what we learned about concavity, when the second derivative is negative, the function is concave down. So clearly, if the function is concave down, and this point is a point where the tangent line is 0, the slope of the tangent line is 0, which we can see here that the value of the first derivative is 0 at that point, so the slope of the tangent line is 0, then that point must be an extrema of the function. Because it's concave down, this is the top of a dome, if you will, and the top of the dome has to be a maximum. Likewise, if we move the point over this side, we can see again we have another extrema value. The first derivative is 0 at this point, but look at the second derivative. The second derivative is positive, and that tells us the function is concave up, which means this is the bottom of a bowl, so that value is going to be a minimum. So that gives us a little bit of a visual insight into what the second derivative test is telling us and why it's telling it to us. So let's move on and see if we can use this in some way. So here we're going to use the second derivative test to find the relative extrema for this function. So we're going to take the first derivative, so f prime of x is negative 15x to the fourth plus 15x squared. Now, a peculiarity of the second derivative test is that we have to use the critical numbers from the first derivative as our inputs into the second derivative. So we've got to find the critical numbers for this. So we set the first derivative equal to 0 and find our critical numbers. We're going to go ahead and factor out a negative 15x squared here, which gives us x squared minus 1. So here we know our critical numbers are going to be 0, the first one is 0, and we have negative 1 and 1. If we solve this for 0, set this equal to 0 and solved, x squared equals 1, square root of 1 is plus and minus 1. So our critical numbers are 0, negative 1, and 1. Now we can go on and take our second derivative and use that with these values. So we have negative 60x to the third plus 30x. That was supposed to be an equal sign in there. And we can now go ahead and evaluate this at these values. So let's just do this, and we'll have negative 1, we'll have 0, and we'll have 1. So let's start at negative 1. Negative 1 into here, that's negative 1 to the third is negative 1. Negative 1 times negative 60 is 60, plus 30 times negative 1 is 60 minus 30, so that's a positive value. So if the second derivative is positive, it's concave up. And if it's concave up, we have a minimum. So let's go ahead and evaluate at 1. Negative 60 times 1 is negative 60, plus 30 is negative 30. So this is concave down, and so we have a maximum. Now at 0, the second derivative is 0, so it fails. So we have to resort back to the first derivative test. So if we put in a negative 0.5 and a 0.5, we see that the function is positive and positive, so it's neither a maximum or minimum at 0, so we only have two extrema, here and here. So let's move on to the next section.